Hi, all APSET2020 chemistry aspirants. Hope you all done well. So here in this video, we are going to analyze each and every question of chemistry paper 2 with best conceptual analysis in the way of justifying the answers. So watch the video completely. Now just look at the first question. The elements A, B, C and D have the following electronic configuration. The simplest question here is given. So just look at the valency electronic configurations. The elements which belong to the same group here 1 and 2 are having general valency electronic configuration as NS2 and P1. That's why they are belong to the same group. Okay, right. The second one, the molecular orbital electron configuration for X anion is. So try to count the total electrons given in the molecular energy orbitals. Okay, right. Sigma 2s2, so 2 electrons, and sigma star 2s2, 2 electrons, and here the bonding 2px and 2py having 4 electrons. Now sigma 2pz, that is having 2 electrons, and antibonding 2px and 2py is having 1 electron, so total of 11. Now the ground state energy levels having the bonding 1s orbital has 2 electron and anti-bonding 1s orbital having 2 electrons, so total of 4. Now the sum equals to 15. So here N2 minus belongs to 15 electrons because each nitrogen contributes 7 electron and the negative charge contributes 1, so total of 15. So our option is B. Now the next question match the following. Here we have the question is given based on HSAB principle, which is very important for CSIR degree lecturers and set and so many examinations. So here beryllium plus 2, which is a hard acid, whereas trialkylphosphine is a soft base and platinum plus 2 is a soft acid, and the base here R2, that is ether, is a hard base. Now just make the combinations. Okay, the next question, the shape and expected hybridization of BrO3 minus and HOCl ore. Now try to look at the hybridization of BrO3 minus, where bromine is the central atom and which is having the general electronic configuration NS2np5. Now try to fill up the electrons here in its valency orbitals. Okay, now in its second excited state, the 2 electrons from p orbital just moves into d orbital. Now you can see we have 5 unpaired electrons, right? So the 3 unpaired electrons will make sigma bond with 3 oxygens, and the other 2 electrons can make pi bond with 2 oxygen atoms. The other oxygen atom bears the negative charge. Now from this we can say that we need to consider the sigma bonded orbitals only for the hybridization. In this case 1 s orbital and 3 p orbitals are involving in hybridization or in the making of sigma bonds. That's why BrO3 minus is sp3 hybridized, where it is having one lone pair. So sp3 hybridization with one lone pair is expected to be pyramidal. So BrO3 minus pyramidal with sp3 hybridization. Now just look at HOCl, where oxygen is the central atom and which is having general electronic configuration NS2np4, where the p orbital is having 2 unpaired electrons. Okay, right, and these 2 unpaired electrons will make sigma bonds with hydrogen and chlorine. You can see the involvement of s and 3 p orbitals which are making sp3 hybridization with 2 lone pairs. You can see one here and one here, and which leads to angular geometry or shape. So you can draw like this. Okay, right. Now third option is the correct answer. increasing p character of the orbital of which or overlaps with the orbital of F2 form IF bond in IF3, IF5 and IF7. Just do the same thing. Just try to find hybridization. For IF3 it is sp3d, for IF5 it is sp3d2, for IF7 it is sp3d3. Now you can see the D character is increasing from left to right. So whenever the D character is increasing, simply P character decreases. So in this case, we can simply choose the third option where the P character increases from IF7 to IF3. Okay, the next question. So the correct arrangements of chlorine, sulfur, phosphorus and silicon in increasing order of their electron affinities. So first thing, just let me know what is electron affinity. So simply whenever the electron is going to add to the outermost valency shells of an atom or molecule or ion, the energy releases from that atom or ion or molecule, that is called as electron affinity, right? Now, so when we look at the basics or basic trends, electron affinity increases from left to right in a period. And the second general trend is always the halogens have highest electron affinities. And third trend is when you move down from top to bottom, electron affinity decreases. So based on these trends, we can say that chlorine must have highest electron affinity. Okay, so the next one must be sulfur. Why? Because it is next to the chlorine in that period. Okay, now here is the question, that is which is having highest electron affinity? Is it silicon or phosphorus? Based on this concept, the question might be given, because so many choose the answer as the first option because they will go with this general trend. But in the general trends, we may have some exceptions. In that, this is the one case where you can see silicon is having the valency electronic configurations as so like this ns2 np2, and the phosphorus is having the valency electronic configuration as ns2 and np3. Okay, now if extra electron is going to add to the phosphorus, okay, so to make it as p minus, then what is happening? So the extra electron must be paired up with one of the unpaired electron in that p orbital. So the electron which is already present in the orbital will make repulsions with this incoming electron. That's why the electron affinity is less to add that extra electron to the phosphorus. When we see that silicon, the electron can easily add it to that empty p orbital, okay, and which is going to make completely half filled and which is the stablest electronic configuration. That's why here the highest energy is released from the silicon when we compare to the phosphorus. So what is the correct order here? So phosphorus is less than silicon, which is less than sulfur, less than chlorine. Option D is the correct one. Okay. Which one of the following complexes show spin crossover? So this question is also given many times in CSIR exam. On this complex, you can see so many questions in CSIR. So where 1,10 phenanthroline, which is the ligand which can switch its low spin and high spin nature by just varying the temperature. So that's why option C is the correct answer. Okay. Next one. Which of the following octahedral complexes possess enantiomerism? So just remember that metal with a bidentate ligand. So a metal AA3 type of complexes always show enantiomerism. So here you can see oxalate is a bidentate ligand and ethylene diamine is a bidentate ligand and phenanthroline is also bidentate ligand. That's why all these complexes can show enantiomerism. Whereas if you look at the trans complex of iron, where you can draw the trans complex of iron like this. So here is the water molecule and here is the water molecule, right? So if you try to draw the another structure of this, so this is the one you can draw, H2O. Okay, so these two are absolutely same, there is no difference, but the same complex, that is a cis complex, here is a chlorine, what we say, water, H2O and H2O, so which can have its a mirror image, that means an enantiomeric pair. So simply the trans complex is not going to make its enantiomeric pair. So 1 2 3 are correct, so option A is the correct answer. But if we have given with the cis here, then all four complexes might be involved in enantiomerism. Okay, right. The next question, the correct spinel structure of CO3 CO4 is. So just look at this question. Here on this question we have that means the same kind of question in csir examination, so where the CO3 CO4 is a normal spinel. Okay, so for the normal spinels, the general representation is given like this: A plus 2, B plus 3. That is, the metal with plus 2 acceleration state occupy in tetrahedral holes, and metal with plus 3 acceleration state occupy in octahedral holes. So based on this, you can see which is the correct case. So here cobalt plus 2 tetrahedral hole and 2 cobalt plus 3 octahedral hole, and that's why option A is the correct answer, because CO3 CO4 is a normal spinel. Okay, right. The next one, arrange the following complexes in the increasing order of lability. So first thing, how can you define the lability? So we have so many definitions, but here for the simple words or simple understanding, we can say that if we have metal and ligand, if the ligand, that means metal ligand bond is easily broken, and if it is replaced with another ligand, then we can say that metal complex is labile complex. Okay, so the easiness of breaking and making a new bond, that is a substitution of ligands in a metal complexes, leads to lability. Okay, right. And just remember that here we have given one transition metal complex, and all other three are non-transition complexes. So the transition metal complexes are more inert than non-transition metal complexes. Okay, based on this concept, we can say the vanadium complex is the least inert, least labile in the given complexes. And we can also see vanadium is in plus 2 acceleration state with the D3 electronic configuration with strong field ligands. CO ligands are there. We know that CO can also act as pi accepting ligand. So due to the pi accepting nature, CO can make a sigma bond and also a pi bond by just dragging the electrons towards it from the metal. So here you can see the two bonds, just like two bonds. That's why it is very difficult to cleave that CO ligand. So we consider that vanadium carbonyl as a inert complex. Okay, now just try to look at the non-transition complexes. So if you look at non-transition complexes, which should be taken to decide the lability. So simply just remember the cationic charge and also cationic size. Okay, so just remember the size, or what we say, charge, inversely related with the lability. Okay, so here just try to give the accretion state on phosphorus is having plus 5, silicon is plus 4, and stibinum is in plus 2 acceleration state. So the order must be stibinum plus 2 is the most labile, then followed by silicon plus 4, followed by phosphorus plus 5, followed by vanadium complex. But the options are given wrong here, so you may get the marks for it. Okay, next question. Match the following. Lanthanides. We can say lanthanides can show the different metals of lanthanides can show used in atomic battery and metallothermic reactions and luminescent lamps and paints. So here praseodymium 147 is also used in atomic battery and luminescent lamps and also in paints. Cerium tungsten. Tungsten is also used in luminescent lamps. So that's why the matching is very difficult, because each and every option is can be matched with more than one options here. That's why I think you may get the marks for that question. Next question. Match the list 1 compounds with list 2, that means acceleration state of cobalt. Here, so just look at the simplest complexes first. If you look at the second one, so sodium plus the ionic sphere, where the cobalt complex is with -1. We know that CO ligand is a neutral ligand. That's why cobalt must be with minus charge. So the second combines with the first one. Right. And next, try to look at the fourth one. In fourth one, CO ligand is neutral ligand. That's why cobalt must be with 0 acceleration state. So here fourth one combines with 2. Okay. And next one, third one here. So where sodium is in, that means 4 sodiums are having charge of +4, so the coordination pair is having -4, where S2O3 is having -2, so simply cobalt is in +3 oxidation state. Okay, and now just look at the first one, NCS, where nitrogen is having minus charge, and where ammonia is a neutral ligand. So if you look at the ionic sphere, where SO3 -2, that's why the coordination sphere is having +2 acceleration state. Whenever this -1 moves to here, cobalt is in +3 oxidation state. Okay, so just combine them. Now just look at the 15th question for the molecule given. So this is the copy paste question from CSIR December 2012 examination. So simply the first one, HNMR has singlet at 5.448 and 3.18, because at room temperature the 5 hydrogens on CP ligand can rotate freely, and that's why they will give only one singlet. Okay, and now it is having higher CO stretching bands at 1950 and 1860. So 1 and 3 options are correct. So A is the correct answer for it. Okay, and next question, the pair of lanthanides with the highest third ionization energies. So it is very important to remember the electronic configurations of lanthanides and actinides, because we may get the questions on the electronic configurations. If you know the electronic configurations, it is easy to find the correct answer. So here europium is having the valence electronic configuration as 5f7 and 6s2, whereas yttrium is having 5f14 and 6s2. So the third ionization energy is very high, because europium is having half filled f orbital and yttrium is having completely filled f orbital. That's why it is very difficult for the third ion to remove the third electron. So that is the third ionization energy is very high. So option B is the correct answer. Now in the hydroformylation reaction, the intermediate, so now just look at the intermediate here, where which is having CH2 and CH3. Here is a CO. Now CO migrates here, and which can make CO, C double bond O, CH2 and CH3, that is acyl group. So forms acylated product by migration. Option A is the correct answer. Okay, now match the following compounds with their total electron count. Now just try to check osmium here. Osmium belongs to iron, and each osmium contribute 8 electrons, and how many of them? So 10 are there, plus each carbon contribute 4 electrons, and each CO contribute 2 electrons. How many of them? 24 are there. And what is the charge on it? -2. So we need to add 2 for it. So total 134. Now, so just look at the second one. So 4 into 8 plus 5. Okay. So just wait a minute. Now here nitrogen is having, that is elemental nitrogen, contribute 5 electrons. Okay, and each CO contributing 2, so total of 24, and which is having -1 charge on it. So we need to add 1 for it. So total 62, but here we have given with 74, so one option is given wrong. Now the third one, so each hydrogen contribute 1 So total of 2 from that hydrogens. And now 6 osmium, 6 into 8 plus 8 into 2. So total of 86, we may get 86. Now for the fourth one, osmium, 7 into 8 plus 21 into 2. So just we can get 98, I think. So one option is given wrong. So just pick the correct answers. And you may get the mark for this question. Okay. So simply for that elemental elements which are in the complexes or clusters, we need to take their valency electrons for the total electronic count. Okay, right? And if you like this video, please click on like, and if you are not subscribed our channel yet, so do subscribe. And if you are interested, you can visit and join the chemmasters.online website for the best online courses, where you can also practice very high standard online test series to boost your success rate. Thank you very much.